Welcome everyone, and thank you for joining us today. My name is Uriol Esquivias, and I'm business developer at Nextmol. For those who maybe don't know us, Nextmol is a computational chemistry company, and we work with specialty chemical companies to accelerate their research and innovation using molecular dynamic simulations and machine learning. Today's session focuses on how evaluate bio-based surfactants as alternatives to conventional ones without committing to a full experimental campaign upfront. We published a study on this topic last year in the SOFW journal, and today we're going to walk through the case in detail. Specifically, we'll show how molecular dynamic simulations can be used to calculate interfacial tension and solubility for sodium lauryl sulfate and sophorolipid alternatives. Presenting this work is Dr. Javier Ortin, application engineer at Nextmol, and one of the authors of this study. Javier holds a PhD in computational chemistry and works daily with our clients on exactly these kinds of projects. Just before that, I want to mention that you can pose the questions during the talk and we will answer in the end after the presentation and the demo of the platform. For your information, the session will be recorded, but your questions or your names won't be recorded, only the broadcasted video. So with that being said, Javier, the virtual floor is yours.
Okay, thank you, Uriel. Um, this is how a traditional R&D scheme would look like in today's home care industry. Currently, we start with a pool of molecules which are candidates to form part of our final product because of some physical-chemical properties that can be interesting for it. So after identifying these molecules, we have to start with an iterative process in which we have to synthesize or purchase our molecule, and then we have to test its properties. We have to repeat this process over and over again until we find a molecule that displays the appropriate properties to enhance our product. This iterative process is the main bottleneck of nowadays R&D processes and can be quite inefficient and time-consuming. According to a study by McKinsey, the commercialization time of a new product can take up to 14 years, and the success rate of these research processes never reaches the 50%, which makes a lot of companies feel that these research processes are potential risks in their economy. However, this success rate can be improved and this commercialization time can be reduced through the adoption of tools like computational chemistry and artificial intelligence, which nowadays have been adopted by many companies in the home care industry. This is how a R&D process would look like with the adoption of these kind of tools. So we start with the same pool of molecules, of the candidates, and instead of going to the lab and starting with the synthesis and the testing, what we do is that we create computational models of these systems. Here we do physical representations that allow us to predict the physical-chemical properties without having to synthesize them. Then we can identify the best performers, and with those best performers, then we go onto the lab. This is translated not only into a high amount of save time, but also into a less amount of chemical waste. This is how a computational chemistry protocol would look like. Here we have the union of several nodes, in which the green nodes correspond to molecules. This is just the idea of a molecule in vacuum, which are the molecules that at the end we want to make, we want them to be part of our system. Then we have these yellow nodes, which we call system operation functions, which will help us to transition from these molecules in vacuum to chemically relevant systems, complex systems. Then we have these pink nodes, which are simulation nodes, which will help us evolve from these idealized and artificial initial structures to experimentally relevant structures at a certain pressure and temperature. And finally, we have these green nodes, which are analysis nodes, which will take the information from the previous node and will calculate the physicochemical property of interest. As we said, one of the advantages of these techniques is that we can build complex chemical systems. As for example, we can create a layer of surfactants that is right at the interface between an aqueous phase and an oil phase. This way, we can, for example, study the interfacial tension of this interface with these surfactants right at the interface. Also, one of the benefits of these protocols is that if we want to now change the molecule of a study, this is just as easy as substituting this node by another one. And this way, we enable the high throughput screening of many molecules and their properties quite fast. Why is it interesting to perform in silico experiments or computational chemistry simulations? So according to our experience in the last years in the home care industry, researchers are trying to obtain detergents that have a higher cleaning power, that are more environmentally friendly, while at the same time they are trying to work with lower temperatures and with lower dosages. So basically right now the researchers in the home care industry are trying to find an ideal detergent. Many times this is achieved, or they are trying to achieve this through the substitution of classical components like the laureth 3-sulfate, which at times these components can have a fuel-based origin, by other components that are more environmentally friendly, that are bio-based, or that are biodegradable. And one example would be sophorolipids. Sophorolipids are molecules that are produced naturally by yeasts in a with a very high performance, and that are formed by the union of a sophorose group and a fatty chain acid. The research of this species has been active for a quite long time now, and experiments have been performed trying to measure the height of the foam formed by detergents that incorporate this molecule, or also the drop in the interfacial tension when using these molecules. So this substitution of these classical components by the innovative ones is going to bring a lot of iterations and a lot of experiments, and this is where the in silico experiments can really boost the productivity and improve the efficiency of the process. So today we are bringing a case study just to showcase how this can be performed. We are going to show how the substitution of this classical surfactant, laureth 3-sulfate, can be assessed on some properties when we and we are going to do so by the substitution by this acidic sophorolipid and the lactonic sophorolipid. We are going to focus on two different properties, how this substitution affects them, and they are the interfacial tension and the solubility. All the information that I am going to show next is part of an article that you have the reference here, and if you want more information, you will find a more detailed version in the article. So as for the interfacial tension, what we did is that we built an aqueous phase in contact with an oil phase, and right at the interface we set a constant coverage of the surfactants that we can see here, that again they are laureth sulfate, acidic sophorolipid, the lactonic sophorolipid, and here we have a mixture or a blend of both sophorolipids. We resorted to molecular dynamics, a technique that allows us to model every single atom of the system, and that provides physical, it's based on physical models and provides the physicochemical properties of these molecules. And we will compare these results with the experimental values that are extracted from the literature. So what we can see is that indeed we are able to predict qualitatively the trend in the reduction of the interfacial tension when substituting one component by another. This is, we can see that The highest value is provided for lauryl sulfate, this is the acidic sophorilipid, and finally the blend of sophorolipids. And we can see that this trend is exactly the same one that we see in the experiment. Quantitatively, the values are not quite there yet, but this can be attributed to many reasons, for example, the differences in size and time scales between the simulation and the experiment. However, the important point is that indeed we can capture these trends, and therefore, given this pool of candidates or molecules, we can identify which will be the best performers. So in the wet lab, the scientists can focus only on the best performers. Also, interestingly, we have this red column here, which we said that corresponds to the lactonic sophorolipid, and this could not be registered in the wet lab because of technical difficulties related to the lack of solubility of this species. So this is another advantage that molecular dynamics brings to us, and it's that we are able to make simulations and obtain results for these properties that, for technical reasons, cannot be obtained in the lab. Then, as for the solubility, we studied how different surfactants can behave in different solvents. To do that, we resorted to the Hansen solubility theory, which is a theory that is used on a daily basis in the lab. And as you can see here, we have here points that correspond to solvents. So each solvent has 3 associated Hansen solubility parameters, and thus we can represent one solvent as a point in a 3-dimensional space, where each axis corresponds to its Hansen solubility parameter, the polar parameter, the dispersion parameter, and the hydrogen bond parameter. So what we did is that we selected 20 different solvents that sample this Hansen solubility space. And once we have selected these 20 solvents, that at first they don't have to be solvents that we are interested on. We just want them to sample this space. So once we have selected them, what we do is that we perform molecular dynamic simulations in which we have our surfactants in these solvents. Then in the simulations, we try to tell apart 2 different behaviors. A behavior like in solvent A, in which the surfactants, after some time, are not aggregating, meaning that the surfactant in this solvent is interacting quite nicely, and therefore this is a good solvent for this surfactant. And then we have solvent B, in which the surfactants, as you can see here, are starting to aggregate, meaning that they are trying to avoid the interactions with the solvent, and thus we can identify this solvent as a bad solvent for our surfactant. Thus, once the simulations have been performed for all solvents, we can identify its solvent with a green dot, if it's a good solvent, and a bad solvent with a red dot. Once this has been performed, what we can do is that we can try to fit a double sphere or 2 spheres in this space, in which we try that these spheres capture all the good solvents. If we are able to do this successfully, then what we have achieved is the obtention of the Hansen solubility parameter of the surfactants, which are located right at the center of the 2 spheres. Typically, the theory of solvent only manages, the Hansen solubility theory only manages 1 sphere, but in this case, since we are using a surfactant which has both an hydrophilic and a hydrophobic part, then it's appropriate to use 2 spheres. Then now we have obtained a model that has located the Hansen solubility parameters of these species, and this enables to now predict whether our surfactant will be soluble in any other given solvent if we have an experimental record of the Hansen solubility parameters. Let's illustrate this with an example. So we can take the handbook of the Hansen solubility parameters, and we can select 2 solvents of our election. These solvents can be represented as dots, as you can see here, for solvent A and solvent B. And then we have to assess if this solvent is inside or outside the solubility sphere. In a case like this, where this solvent is inside our solubility sphere, we will be able to predict that our surfactant is soluble in this solvent without the need to go into the lab and test this. And on the other hand, we have this other situation in which this solvent, its point, is located outside of the solubility sphere, meaning that we already know that this surfactant is not soluble in solvent A. So we applied this procedure to our surfactants, our innovative surfactants, the acidic sophorolipid and the lactonic sophorolipid. Here you can see the list of good and bad solvents, and this allowed us to obtain the two spheres of solubility. Just as a reminder, here what we have is that the green points correspond to simulations in which we observed low aggregation, meaning that for the green points, this is a good solvent for our surfactants. And on the contrary, that the red points correspond to simulations in which we observed high aggregation and thus poor solubility. Just a note here, it might look like some of the red points are inside the sphere, but this is a matter of perspective. Just remember that these plots are 3D plots. So actually, these points are either in front of the sphere or behind of the sphere, but these red points are never inside the sphere. Also, just as a curiosity, this fact that we find that regarding the solubility of surfactants, this is something that can also be predicted in an early stage of the simulations of the interfacial tension values. For example, here we are looking at a top view of the interface between the water and the oil, in which we have omitted the oil molecules. So here you can see that the lactonic sophorolipid is less homogeneously distributed than the lauryl 3-sulfate, which is already telling us that this sophorolipid is going to display worse solubility than its counterpart, than the lauryl 3-sulfate. Then jumping back onto this scheme with the solubility spheres, there's one important part of the Hansen theory that we can use, and that is quite interesting. The Hansen solubility theory states that if we have two solvents that are on opposing sides of a solubility sphere, like in this case, if we select as a reference the red sphere, we have water and heptane on opposing sides of the sphere. Then a mixture of them will be a better solvent than any of those solvents on their own. So we did this test. We did the simulations for heptane and water on their own, and we obtained that these are some of the worst solvents for the sophorolipids. And then we used simulations in which the solvent was a mixture of water and heptane. And indeed, what we observed that this is a better solvent than any of those by separate. It can be surprising to think of a mixture of water and heptane. However, it's important to note that here what we are observing is that our sophorolipid is acting as an emulsifier, and thus is able to break this immiscible dynamic. Just now on a final note, all of these techniques can be coupled to artificial intelligence, and this is something that we work on a daily basis. So, for example, this is a paper that is the product of a collaboration between our R&D team and the research and innovation team by L'Oréal, in which a machine learning model was trained based on the molecular dynamic simulations that were aiming to predict the glass transition temperature of a polymer. Thus, what we obtain is a machine learning model that is able to instantaneously predict the glass transition temperature of a biopolymer with an accuracy which is pretty much the same as the one from the molecular dynamic simulations. This huge speed up in the obtention of the value enables the high throughput screening of thousands of polymers just using this machine learning model. So, as a conclusion, we want to transmit that these technologies, these techniques, are not exclusive for the academic environment, but instead these are mature technologies that can be used and that are being used by many companies in the home care industry. Also that these companies are using these technologies because their use is translated into a significant saving in time and cost, and also in we avoid the use of or the generation of excessive waste, of chemical waste. And finally, that as we have seen, we are able to model large and complex formulations, and we are able to provide useful properties like the interfacial tension of a surfactant or its solubility in different solvents just through computational models. So this is all for the technical part, the talk. And now we would like to make a really brief demo about our platform so you can observe how you could be using these techniques in your own research.
Thank you very much, Javier, for the exciting talk. So as Javier mentioned, now we will do a brief demo of the platform, of the Nextmol Lab platform, so you can see how yourself you could do the same simulations quite easily. And after that, we will answer the questions that may arise. If you have like some other specific questions, you can also write an email to Javier or to contact us. I will also like leave my email here, and you can contact me too. So with that being said, Javier, I'm going to give you again.
Okay, thank you. Okay, so this is the main page of the Nextmol modeling platform. This is the dashboard. This is where you will see a summary of all your jobs, projects, analysis, and computational resources that are in use in your account. So this is the starting point, and we can, let me zoom in a little bit. Then we can go on to this icon and display the sidebar menu, in which we can see the different parts of the platform that we can access. So we are going to skip this dashboard because we have already seen it, and instead we are going to jump onto the Projects tab. Here you will find the different projects in your account, and this can be thought of like a folder system in which you can make folders for different projects that you may have. In this case, we are going to jump onto the screening of interfacial tension of surfactants. This is the first part of the talk that we just saw. In this case, we have divided this project according to the molecule that is being studied. So we can see here that we have SDS, SLES, and also SLS. So in the project tab, in the project section, we have three different tabs. An information tab in which we can provide a name for the project and also give a brief description to enhance the organization of the project. Then the different experiments that we have. And finally, the jobs that have been completed in this project. So let's jump, for example, on the experiment for sodium lauryl 3 sulfate. And here, what we can find is, again, three different tabs. An information tab that, again, allows us to give a name to this experiment and provide a description. The workflow, which I will be commenting on next. And a section of completed jobs that will display which jobs have been completed using this specific workflow. So for the explanation of the workflow, let's illustrate it with a completed job. We can click on this one, for example, and we are currently at the workflow section inside of a job. So here, what we are trying to do with this union of many nodes, we are trying to create this chemical system that we showed in the talk. We want to create a layer of surfactants that is right at the interface between an oil phase and an aqueous phase. So we start from a molecule that we can visualize. For example, we can click on the node of the molecule and click on View Step. And here the user can visualize the molecule that is going to be used. Then nodes 1 to 6 aim to create a layer of surfactants in which we have an ordered layer of lauryl 3 sulfate molecules, and we can visualize that by clicking again on this node and clicking on View Step. Here we can observe that we have a layer of 40 surfactants in a surface of 80 per 80 Armstrong. Then after that, we can add a layer of water molecules. Again, we can visualize this water molecule by clicking on View Step. And here we can visualize it. And we can create a layer and add to this layer as layer of surfactants. And this way we can easily visualize it. Finally, we can duplicate the surfactant layer and add the oil phase. And this way we will obtain something like this. Here we can tell apart the aqueous part, the oil phase, and finally the surfactants that are located right at the interface. This is quite an artificial and idealized structure that will later on be modified through the simulations of GROMACS, which are represented by these pink nodes. So for example, in this case, we can jump onto the production node, which is the last node that we are interested in. And here we can see a much more realistic case for what we would be able to see if we could zoom in to the lab. So here we can also play the film to visualize how the simulation evolved. I think that it's important that that in this type of representations we have to tune the visualization, which in this case using XML modeling is quite easy. So in this case, for example, let's hide the oil molecules and just stay with the water molecules and the surfactants. To do so, we can click on this icon. This sidebar menu will open, and we can add a new representation. We can select to represent only filtering with residue names, and then we can select only to represent the water molecules and the surfactants. And this way, what we can obtain, sorry, let's do it again. Okay, okay, I selected the one that is not the surfactant. Okay, now we can visualize how the interface is behaving with the surfactants. And we can either go to the beginning of the simulation, and we can also go to the end of the simulation. There it is. And we can see how the surfactants are interacting with our surface. And finally, after the production node, here we have the analysis node. In this analysis node, this is where we extract the relevant information. This is the interfacial tension, which will appear in the tab of analysis. Then we can click on the interfacial tension of SLES, and here we can observe under the tab results the value for the interfacial tension for this surfactant at this coverage of the interface. Let's suppose that we would like to study other surfactants that are not lauryl 3 sulfate and that are not implemented in the platform. So creating our own molecule is super easy in the platform. We can go to the sidebar menu, clicking on this icon, and then we can go to the molecules section. Here you will find a summary of all the molecules that we provide to you in our catalog. But if you want to use any other molecule, you can click here on New Molecule. And here you can insert the name of the molecule. In this case, we can create, for example, 1,2-propanediol. We can save the name, and then we can jump onto the Designer tab. Here you will find a chemical catcher that is like any other commercial package that you might have used. And here we can draw our molecule. So for example, for this case, we can do like this. And we already have a representation for 1,2,3-propanediol. We can save it and convert it to 3D. And after a few seconds, we will be able to observe the model for our molecule. Let's reload. Okay, here it is. And finally, we can jump onto the potential tab, in which we will describe the physical behavior of this molecule. This is the strength in the bonds, or how flexible this is. And if the user does not have a description of its own, it can be easily generated with an XML platform, just like this. So once this molecule is generated, then we can go back to our project. We go again to the screening of interfacial tension of surfactants. We can click on our project, sodium lauryl sulfate, and here we can edit workflow, click on the molecule that we want to substitute, and replace it. And then we can click on, for example, 1,2-propanediol, and the potential is still being completed, but here it should be ready. Yes, indeed. And just like that, now we can calculate the values of the interfacial tension using another molecule, even if for this case 1,2-propanediol is not the most interesting. Then what we can show also is the other project that we displayed in the talk, and this is the calculation of the solubility of species. So in this case, we can go back to the projects, and we can click on solubility of SLES. And here we have different projects in which we are changing different experiments in which we are changing the solvent in which we do this study. So we can click on SLES in water, and here you can see a much simpler workflow in which we fill a simulation cell with our surfactant and with water. Then we apply the simulations and we extract the solubility parameter. Then we can check the job, and once again the user can visualize both the molecule and also the filling of the cell. This is it. And also the user can go down to the production node and can compare how aggregated the molecules are in the beginning and at the end of the simulations. So for example, in this case, we have that this is the first snapshot of the simulation, and then we can jump onto the last one and see that indeed something has happened. Once again, we can help the visualization with some tuning. So we can hide this visualization and we can just stick with the visualization of the lauryl sulfate. So now it's much easier to observe that at the end of the simulation, the lauryl sulfate is aggregated, meaning that this is not the best solvent for this surfactant, and that if we visualize the beginning of the simulation, indeed an aggregation process has happened. So next, I would like to show you how we can calculate other properties. We at Nextmol, we offer a set of pre-assembled workflows for the calculation of properties for both surfactants and polymers. So all of these are workflows that you can use, and for the calculation, for example, of the radius of gyration of a polymer or the persistent length of a polymer. And also there are workflows for the calculation of the absorption of surfactants on a surface. All of this is pre-assembled, but if you would like to study any other property and a workflow is not pre-assembled here, we can prepare a workflow exclusively for your issue and adapt it to your needs. And finally, just to end this demo, we would like to show that we have a documentation page in which everything is well described in order for the user to understand how every single part of the platform works. And also the user will be able to find, for example, which post-processing functions we have, or some tutorials which will help with the first steps of using the platform. So I think that with this we can end this part of the webinar. Maybe, Uriel, we can jump to the questions.